All right, here we got a fantastic double loop Hot Wheels track. It's just totally awesome. So in here we have the car and it has a little spring launcher. The spring launches the car. It's going to go around this loop, the bigger loop, and then goes around a smaller loop and then just keeps on going. And what we're going to do is we're going to find out a couple things about the situation. So first things first, we're going to label a couple things here and make some values here. Obviously this loop is taller than this one. Let's say this loop is 40 centimeters tall. And let's say this loop is 30 centimeters tall. And inside of the little spring launcher here, let's say this thing was pulled back. Well, let's go with 6 centimeters. So it was pulled back 6 centimeters to launch the car. And let's say this is we'll say it's a 60-gram Hot Wheels car. Okay, now we're going to find out a few things here. Now, the car is going to come along, get shot out, goes around here, and then around this one. Now, obviously, between the two loops, the harder one to go around would be the bigger one because it's taller. So let's say this big loop, it actually goes around with the minimum speed possible to actually make it around. Okay, so it makes it around that one. If it makes it around this one, obviously it's going to go around this one. We're not going to lose any energy to anything like that. It's all be idealized, so it's going to be fantastic. And let's use this idea to find out a couple things. Let's find out what is the key value inside the spring, but also what is the speed at the top of this loop, as well as what is the normal force at the top of that loop. Okay, so we'll bring some circular motion stuff as well. And so I'll piece these things together. Now, there's energies, there's forces involved with this. So let's just start with simple things that we can find and work with it. Now, I can't really do too much here. All I know is the X value and the mass. I don't have the K value here, so leave this alone for now. I go up here. I've got the height, I've got the mass, so I can find the potential energy here. But it doesn't just have potential, it also has kinetic, but I don't know how fast it's going. But this right here helps me out to find the speed at the top of the loop. Because I know if I'm at minimum speed with circular motion, that's when Fc and Fg are equal to each other. So my mv squared over r has to be equal to my mg if this is my minimum speed. We've done this before with circular energy. Or not circular motion, and incorporating energy with it. So if we do this, we know that the m's cancel out, and we've had this before. The minimum speed required would just be the root of rg put together. So I know the radius is 20 centimeters because it's a 40 centimeters tall loop. So I got the radius of 0.2. I can times it by 9.81, and then don't forget to square root. And it's going 1.4 meters per second at the top of this loop. So here it's going 1.4 meters per second. Well, now that I have the speed at the top of that loop, I can find the kinetic energy there. I also know the height of the loop and the mass. I can find the potential energy up there. I can put those two together, and I've got the total energy. And once I have the total energy there, I can put it anywhere. So let's just start by finding the kinetic energy in there. So the kinetic energy for this first loop, kinetic energy would be the 1/2 mv squared. I'm going to put this in for my v value. So I can take that, times it by, or square it, times it by 0.5, times it by the 0.06, and we've got 0.059 joules of kinetic energy. I'm also going to find the potential energy up there. That's just mgh. I've got the mass of 0.06. I can times it by my 9.81, times it by the 0.4 for the height of that loop, and I've got 0.235 joules. Okay, now what I'm going to do is I can add those together, and that'll be my total energy. So that'll be my energy total, and that'll be the total everywhere. So I add the two together, and we've got 0.294 joules of energy, and that is my total energy absolutely everywhere in the situation. So easiest thing to do right now is to take that energy and put it into the spring, because that's where it came from in the first place. So if I take that 0.294, so I got the 294 and I make that equal to 1/2 kx squared for spring energy, I can find my k value. So I take that, I can times that by 2, and I can divide that by my compression, which is the 0.06, don't forget to square it, and I've got a k value of around 164 newtons per meter, and that is the k value for my spring. All right, so that's all taken care of. Now I need to look at what's happening with my second loop. I'm going to find the speed of the top as well as the normal force. Now I know the speed of the top of this loop was 1.4. This one will not be 1.4. Okay, it should be a little bit faster because it's a little bit lower. So let's see what we can do here. Now I do know that the total energy never ever changes, so we can work with that. Okay, so I'm going to look at my second loop. This was loop number 1. So now I'm going to start looking at loop number 2. So for loop number 2, I know its potential energy is going to be mgh, and the height will be the 30 centimeters. So I've got the 0.06, I can times that by 9.81, I can times that by the 0.3 for the height, and I got a potential energy of 0.177 joules. So obviously a little bit less than the potential energy of the taller loop. Now I know my total energy has to add up to the 294. I've got 177. So what I can do is I can subtract the 2 to find out how much kinetic energy there is. So the difference between the two is 0.117 joules, and that would be my kinetic energy. Okay, so the kinetic energy is higher than it was in the other loop, which makes sense because it should be going faster. So make that equal to 1/2 mv squared. I'll make that a little better, squared. And I can solve for my speed at the top of the second loop. So I can take my 0.117, I can times that by 2, divide that by the mass of the car, which is 0.06, and we square root, and it's going around 2.0 meters per second, which is faster than the taller loop, which of course makes sense. All right, speed is taken care of just by using conservation of energy. Now I can try and find out my Fn, and this is where the forces kick in. So I got two forces, of course, acting on the car to go around the circle. Obviously, we have to find Fc. So going a circle, we can find the Fc, the mv squared over r. I know the mass of the car, that's the 60. I know the v, which is 2. I know the radius, which would be the 15 centimeters. Don't use the 30, make sure you use the 15. So I can take my speed, square it, times it by the 0.06 for the mass, divided by the radius of the loop, and we're looking at around 1.57 newtons for circular force. All right, well, there's also the force of gravity at the top of the loop, and that of course is just mg. So I got the 0.06, I'll times that by the 9.81, and we've got about 0.59 newtons for Fg. All right, so let's just sort of piece this together. I need 1.57 newtons for it to go around the circle. And of course, that Fc is pointing down towards the center of the circle, which is the exact same place that Fg is pointing at. So Fg helps you out, which means the track has to supply the rest. So the Fn would just be the difference between the two, which is like 0.98 newtons. So it's the combination of gravity pulling down as well as the track pushing down with 0.98. Those two put together will give you the 1.57 required for the circular motion. So Fn is all taken care of.